Right. Good afternoon, everyone. Thank you for joining today's webinar. The talk is delivered to you by the International Society for Computational Fluid Dynamics, ICFD for short. The ICFD is run by a dedicated team of like-minded volunteers, including myself, who aim to increase the visibility of CFD research. Our purpose is to bring people and ideas together by creating opportunities for knowledge exchange, such as this webinar. We regularly host CFD professionals from varying backgrounds to share their work and perspectives. If you like this idea and format, we invite you to follow us on LinkedIn and Twitter for updates. Also, there are some past events on our YouTube channel, so please feel free to check them out. I will post all the relevant links in the chat for you. Today's event is expected to last about an hour with 45 minutes of the talk itself and 15 minutes Q&A. If you have a question, please post it in the chat. I will collect them and read them out loud at the end of the talk. Today, we have the chance to meet and listen to Dr. Maciej, the founder of Flowfusic. I will post the link in the chat too. Flowfusic is a web-based platform for CFD in a cloud. He did his PhD at Loughborough University in the UK in collaboration with industry, Jaguar and Land Rover. During his doctorate, he worked on multiphase solver for automotive exterior water management. He developed a coupled level set and volume of fluid VOF method in OpenFOAM for large-scale applications. After his PhD, Maciej continued his adventure with OpenFOAM, but this time dedicating himself to cloud computing services with a special focus on machine learning and artificial intelligence applications in CFD, which we have the chance to appreciate today. Maciej, without further ado, the floor is yours.
Thank you very much. Thank you. Yeah, do you see my screen?
Yes, I can see it perfectly.
Okay.
And you're perfectly audible as well.
Okay, thank you very much. Thank you for the introduction, and thank you for giving me opportunity to talk today. So yes, I will be talking about the, so the topic is what do we do when we cannot simulate? And I will start with some introduction from my PhD, showing some examples, how we hit the limit of CFD. And the question is what can we do? And yet there's a lot of artificial intelligence now going on, also in the CFD domains. So the question is what AI or machine learning can offer in CFD. So yeah, my background, I have engineering background, and I graduated from Warsaw University of Technology. I spent more than a year in Paris, in France, at École Supérieure de Physique et Chimie Industrielle. And back then I was doing only experimental work. So I was researching a fundamental, it was fundamental research, fundamental physics. It was a water tunnel. I was doing a PIV measurements of flow behind the sphere in water tunnel. But then I moved to UK. I started PhD at Loughborough University. It was with collaboration with Jaguar Land Rover. It was purely a CFD work. I will be talking a little bit about my PhD to give you some ideas. There is no direct link between the things that I did on PhD and what I'm doing right now. I founded a Flowfusic. It's a web-based platform for CFD in the cloud. What is common between Flowfusic and my PhD is OpenFOAM in general, because I work with OpenFOAM during my PhD, and the platform is based on OpenFOAM as well. But now we are looking for some interesting models, novel methods from machine learning perspective for CFD. Yeah, so my PhD was about exterior water management. So what it is, exterior water management generally looks at rainwater on automotive surfaces. Why car manufacturers are interested in such topic? Well, there are different reasons. From safety perspective, such as driver vision, there's an issue with performance of onboard cameras and optical sensors, and these are very important for autonomous driving. But there are also different reasons, and as always, there are some EU regulations that requires from car manufacturers to report on water management on cars. So basically, we'll be looking at how water behaves on the surface of the car. Of course, we'll be looking at these problems from CFD perspective. Here, you can see a picture of Adrian Gaillard, actually. He's sitting inside the car. He had a talk, I think, 2 months ago. It's just a interesting fact. Okay, so what challenges do we have here from CFD perspective? So in industry right now, we are using, or car manufacturers are using a method, they're using Lagrangian method and thin film method for modeling such a problems. With Lagrangian and thin film methods, you need additional models. You need a model for breakup, you need a model for splash, for rebound, for coalescence. Also the thin film model, you solve a transport equation, but it is there is a 2D assumption, so you don't account for 3D effects. This is why we are looking at a different approach. What if we can resolve the interface, like multiphase interface, like let's say a droplet? We can resolve, and then we don't need any models because we are solving Navier-Stokes equation. We account for surface tension and other terms related to multiphase flow, and we can resolve this interface and have a direct method. So in Lagrangian approach, we assume that particles are small. In Eulerian approach, the particle, the droplet, must be much bigger than our mesh spacing. And this is the main problem, that because when you double your mesh spacing, basically increase your computational cost by 16. And also when we are looking at these phenomena that we see on exterior water management, you will see a big range of length and time scales. This at least 4 orders of magnitude. And when we are looking at the problem of car driving in a car, we basically can distinguish 3 phases. So the first is how water gets to the surface. So we have a droplet impacts. Droplet impacts, we have different splash regimes. So the droplet can deposit without any splash on the surface, or it can splash, and this depends on Reynolds and Weber numbers. And for droplet impacts, we need high mesh resolution. Then in Lagrangian and thin film model, thin film approaches, we use some closing models like rebound models, which works like more or less like this. So okay, when my particle hit the surface, let's take 75% of its mass and put it like to the surface, and the rest emit as a new particle from the rebound. So this is basically what rebound models do. Then we have surface flow. So we have droplets, we have rivulets, we have thin film flow. So one of the examples is when we are looking at a pillar overflow. So we have some water in the front windshield, and then the water flows over a pillar to the side and is distracting the vision of the side mirror. And here we have lower mesh requirements, but actually this is very highly sensitive to contact angle. So you can imagine that water behaves differently when we have hydrophilic or hydrophobic surfaces. And for this, industry uses thin film method. And finally, we have re-entrainment. So eventually the water from the surface gets back to the wake, or it can strip from edge, for example, and gets from wing mirror to the side glass. Here we have moderate mesh resolution requirements. From physical perspective, there is, for example, Kelvin-Helmholtz instability that we are considering here as well. And there are some models for re-entrainment available for these methods. So now when we're talking about practical application, we have a droplet. Let's say that this is our base mesh. So once we have a splash, the secondary droplet can be very quickly unresolved. So the problem is that how fine your mesh should be to capture the secondary droplet. And again, as I said, we can refine the whole mesh, but it increases computational time very significantly, very quickly. We can also try to refine the mesh only in regions of interest, but actually we don't know a priori where our secondary droplets will be. So what we do is usually we use some adaptive meshing. Adaptive meshing basically follows the interface of the droplet, making it computationally much cheaper because we're using high resolution in regions when we want to use. And on top of that, yes, I was using a coupled level set and volume of fluid method. I'm not going into the details of this method, but actually this is the method that outperforms VOF without extra computational cost. I mean, with negligible computational overhead. I use very fast and implemented and derived a very fast interface construction. This is a part of multiphase simulation that this speeds up to 1.8 times the simulation. And also adaptive mesh refinement speeds up orders of magnitude. So we can say that the method is pretty efficient, but due to the physics, it's still very expensive. So this is the example of, we have just we have a side mirror. In this example, we have 5.6 million mesh. This is the base mesh, and we use 2 levels of refinement. So without refinement, the fine mesh is something like 360 billion cells. So it's a very fine mesh. And when you look to the splash, actually, we still don't get the right resolution for secondary droplets. These droplets are pretty big. You might get much smaller droplet during the hits, and we still don't see how the liquid builds up, and we don't see can't get a lot of information secondary droplet. So what we can do, instead of using this as a standard method, we basically can use it to derive a simplified models. So instead of looking for whole mirror and looking how it behaves in general, can take one of these droplets, check how it perform the simulation, as you can see here. Then we have very nicely captured the secondary droplets. By the way, this is a 6 levels of refinement. So you can see in this simulation we have 2 levels. So we needed 6 levels to capture the secondary droplets of these splashes, and then we can do some statistics of the secondary droplets. We can derive the model and use it, for example, in the Mount Lagrangian simulation. So definitely we are able to capture physical phenomena with the method, but we can't use this method. I mean, actually, this is not very likely to be a standard tool in industry due to computational cost. So the question here is what we can do instead if we can't do this simulation as a standard tool. Also, the unresolved simulation, usually you capture fewer details, but also you can end up with wrong phenomena predicted. So you might see deposition, whereas there should be a splash. There's another example that we are deriving a re-entrainment model. So here the gravity acts to the left. As you can see, the film is generating to the left. On the middle line of the swing mirror, you have a slot which injects a water very slowly. So it's a kind of setup. We see a type of Kelvin-Helmholtz instability in high shear regions. We can see some reentrainment from tip of the water. We can see some reentrainment from edge. And actually, based on this, we were able to derive some or validate some more complicated model. Again, this model will be used in simplified methods. So now, having very accurate simulation, but we can't use it as a normal tool, as a standard tool in industry. So now we are looking what can we do, how we can derive models, or what we can do when we cannot simulate. So this is basically, that was my idea for the talk today. And actually, we are looking into the machine learning in CFD, what machine learning can offer in terms of CFD. So we see machine learning right now almost everywhere, in every industry, and it's doing very great job. It's very successful in many applications. And actually, also in CFD, we have a huge increase in the interest. So this is the number of publications about machine learning and CFD. We see that 5 years ago, we haven't a lot, but in 2019, we had a very big number of publications, and this is growing. I mean, this is growing much faster than the number of publications in general. So we see that there's big increase in interest, and we are looking what we can do with these methods. So definitely there's a transformative potential in it. Today we'll be looking at this example of machine learning that we did on Flowfusic platform. So what we'll be doing today is we try to simulate a flow around airfoil with standard CFD simulation, and we'll try to predict the flow, the velocity, and the pressure using only neural network. So there's spoiler alert that we got 1% error in our prediction. So and the neural network simulation runs much faster than the CFD simulation. So I will walk through this example and we'll show how we accomplish this speed up, how we accomplish the neural network simulation step by step. So okay, when we're talking about CFD, we usually follow this path. We have some parameters, input parameters, which is geometry, which is initial conditions, boundary condition, etc. And we use them to set up our CFD simulation. We use CFD solver, and as an output, we have, for example, pressure, velocity. We can have lift, drag coefficient, etc. And today we'll be looking if we are able to replace the CFD part with some machine learning bugs. Because CFD is expensive, and we hope that the machine learning will be much cheaper. So, and with this particular example, I will focus only on geometry. So our input parameter will be geometry. We'll do it for a fixed initial condition and fixed boundary conditions, and we'll be trying to predict or guess pressure and velocity fields using only machine learning. So I will start with some introduction to the machine learning itself. I think this is a very nice definition that the learning problem can be formulated as the process of estimating association between inputs, outputs, and parameters of the system using limited observations. So the key thing here is we have limited observations. We don't want to solve every possible scenario regarding this problem. We want to solve only a few or just a limited number and see if we are able to estimate some association out of it. So there's a short introduction to the neural networks, how they work. So basically, neural networks are inspired by human brain. This is a network that is organized into layers. Each layer consists of a number of neurons. Every neuron is doing a very simple mathematical operation. So basically, in this example, we have input layer, we have one hidden layer, and we have output layer. Input layer will be in this example, four input numbers, and the output layer will be a one number. This will be like yes or no. This can be a binary classifier, this example. What is happening in the middle is all mathematical operation is performed by hidden layer, and every neuron here is doing this operation. So it takes the input, multiply it by some weight, add some bias, and then this output is then passed to the activation function and passed out to the next layer. Activation function is very important in neural networks, and we'll see in a moment why the activation function is important. So ReLU, its rectified linear unit, is one example of activation function which is commonly used in some tasks. So this activation function is pretty simple. We just cut off on negative numbers. So it's a maximum of 0 and x. Actually, this activation function works pretty well for many tasks. So now when we try to get the idea, I mean, as each neuron in each layer is doing exactly the same operation, we can just forget about neurons, we can start talking about layers and assume that we don't do operation one by one, but we have just a matrix that is multiplied by an input vector. And in this way, it's much easier, hopefully, to understand how the data flows in neural networks. So basically, our input is a vector x1 to xn. We pass it to the first hidden layer. Then we multiply it by our weight matrix. We perform the activation function, and we just pass this information to the next layer. We do it until we get to the output layer, which is y1 to ym outputs. So now we can see that if we take out the activation part of our layers, we have just a linear operations on each layer. So if we have a combination of linear operations, we can just do the math and take just a one weight matrix for all the all three layers. This is why we need activation function. Activation functions makes our network nonlinear, and now the network is able to work in more sophisticated tasks. Yeah. So basically, what is neural network doing is taking an input x, performs some mapping of x to the y, and the mapping depends on our weights. I'll be talking a lot about these weights, but we don't know yet what the weights are. So basically, our neural network is a mapping from x to y using some function, which is a sequence of matrix multiplications, and this function is parameterized by W. Now, W is selected by attempting to minimize a cost function. So we define a cost function, or sometimes called loss function. This could be, for example, L2 norm. And this is difference between what the mapping function is predicting and what the ground truth is. So we basically have a number of examples. We have a number of Ys. These are our training examples. We perform this mapping function. We look to the predicted value. We calculate cost of these two. And now having the cost, we are able to perform some optimization. So learning in machine learning, in neural networks, is determination of W. So we're trying to learn W by minimizing the cost function. And we hope that that when we find a minimum of cost function, our mapping function will be something that works more general. For the training, usually a stochastic gradient descent is used. So we basically calculate the gradient of cost function in direction of weights, and we adjust the weights towards the negative gradient. So we can think about this, that each weight is adjusted in proportion to how much it contributes to the overall error. And this improves our prediction accuracy. Okay, and now the question is, we trained our mapping function on some examples. How do we know that this will work outside the examples, outside the set of examples? So there's a universal approximation theorem that states that any function may be approximated by a sufficiently large and deep neural network. So, and also, if we have sufficiently large neural network, which is optimized on sufficiently large number of examples, we can produce a model that is both accurate and generalizable, working outside the set of training examples. So this is the theory, and we are hoping that our network is sufficiently large and has sufficiently big number of examples. So now we know a little bit about how neural networks work. I want to show you an example of a type of layer, the operation that is commonly used in any data that is spatially organized, so especially images. So this is a convolutional layer. So in principles, it's very similar to what we do in CFD in LES filtering. So basically, it calculates an average or do some. It's not an average; it's like a weighted average. Yes, because this 3x3 square has 9 weights. So we take this square, we slide over our input layer, and we perform this operation, and to the next layer we just put the output. What is interesting in this approach is that we actually have a set of 9 weights that we use for every position of this square. So in the network that we seen previously, in a naive approach, we will have the layer that is this big. We have 25 5x5 layer, and each of the neuron will have 9 weights. But instead of each of them having 9, we have just one set of 9 that is shared between them. So this way we are able to have a very sophisticated layer that has not that big number of parameters, and this performs very well in terms of image recognition. And actually, we'll be using this approach in our CFD problem, as we also have spatially organized data. And then we stack the convolutional. So this type of layers, we stack a number of these layers. And then each of the layer is able to predict different or to extract different type of features. So for example, the first set of layers is extracting something like corners, edges, low-level features. But the last layer is able to extract more features with like more complicated, and eventually we are able to guess what number, what digit, what is written on the image. And using this architecture, this is a architecture of the network that won a competition in 2016 in image recognition, and actually it stacks a convolutional layers together, and this network is very efficient in recognizing what is the image. And now we trying to get this idea, and in our case we'll be using something similar, but we will have the converging part. We will take the converging part of previous network architecture, but then we'll do something like similar approach, but going other way around. We'll code this architecture UNet. So we have encoder here and we have decoder here, and we'll put as an input geometry here. This part will extract all information about our geometry and code it to the limited number of features, of parameters. And then from these parameters, we'll be trying to reproduce the images that we are looking for, like pressure and velocity. This part will be responsible for solving our problem for geometry. This part will be responsible for coding our geometry to something that network is able to understand. So now we can go back to the problem formulation. So we have a geometry as our parameters. We have our CFD solver that we'll be using a lot to produce training examples Y, and then we'll fit our machine learning with these Ys and get the predictions and hope that these predictions will be close to our P and U. We'll be able to get the output of simulation. So now some technical details about the simulation itself. We'll be looking at flow around airfoil. We'll be not using any specific airfoils. Instead, we'll be using some parameterization. So there's a paper from 2018 that shows how to parameterize an airfoil, actually any airfoil, using 8 parameters. They gave 8 parameters and the ranges of these parameters. So what we did, we just randomly selected these 8 parameters and generate a big set of airfoils. As you can see, some of them are very bad. Some of them looks actually like an airfoil. So we'll be using these as a input to our network, as something that we want to guess. We'll be using 2D run simulation. We'll be using a fixed velocity 50 meters per second, 0-degree angle of attack. And we'll be using OpenFOAM, and also I will show you how we automated the meshing part of our simulation. Yeah. So what we have to do, we have our geometry of airfoil, and we have to generate a mesh around the airfoil to calculate the flow. But we need to do it in some kind of automatic way. So in OpenFOAM, we basically have 2 options: this block mesh and this snappy hex mesh. Block mesh is for this case is quite difficult to set up. So we used 4 blocks of mesh. I mean, 4 blocks in block mesh. We specified spacing in each block, and actually we provided a list of coordinates on an airfoil to adjust the edges of the block. And this is why even if when we change the geometry, we are hoping that our mesh will deform accurately to our geometry. Of course, when you look to some of these examples that have very, very sharp leading edge, then our block mesh will be very, very wrong in the leading edge. But we can just, if we have very poor mesh, we can just skip the example. So we are able to produce a mesh with y plus below 1 with this technique, and it runs very quickly in 1 second for this example. With snappy hex mesh, it runs definitely longer. We need something like 60 seconds, and it requires more memory because, well, yeah. So snappy hex mesh is computationally more expensive, but it's more robust. The problematic might be a trailing edge. So this is the point to look at. But actually, we were not able to get with y plus to the value that we wanted. Therefore, we stick to the block mesh. And now we have some flow results from the simulation. So we perform simulation of these geometries. So we have pressure, we have velocity, and now what we do, because this pressure and this velocity, they are defined on such a mesh. So we have to get with this information to a more standardized way to get with the information to the neural network. So what we are doing, we are selecting a box around our airfoil. We do some mapping to the regular 100 by 300 mesh, and we produce basically for these fields. We have one field responsible for geometry. So we have one where is the body and 0 outside. And we have a one field for pressure and 2 for velocity, ux, y. And now the geometry will be an input to our neural network. And pressure, velocity x, velocity y, these are expected to be output of our network. And for training, we create this both. We provide this as an input, and we provide this as our ground truth. And the network is trying to learn how to guess the pressure velocity from just the geometry. This is our aim. And now we created a data set with 100 examples for training. We also created a validation set. So validation set, they are the number of geometries that we perform simulation, but we don't use the geometries to train our model, but we use this just to check the network performance during the training phase. So these are the samples that network during learning doesn't see. And if we see nice performance on validation set, it means that our training is going to the right direction. And finally, we have a test set. So we use test set when our network is trained, and we want to see how well it performs after training. So we have 1,000 examples here. We have 200 examples with validation. We have 200 examples with test set. So for training, so we did training on Flowfusic platform. Basically, we have access to Tesla K80 GPU because we recommend using GPU for training. And actually, the training is pretty simple once you have the code for network written. So we use a implementation in Python using PyTorch. It's a popular machine learning framework. And actually, for training this code, you just need to type 3 commands to train it on GPU. From the training output, you can see that we have the training loss. I'm not sure if you see this, but there's a line specifying this is a training loss. And as you can see in every iteration, you also have the information about what is validation loss. So this is these 2 indicators that I said before. And now we have results. So we have 2 examples. There are 2 unseen geometries, left and right. And each of the example on the left-hand side, we have a OpenFOAM result. The right-hand side, we have neural network. this is only a 1,000 examples. This is 1,000 examples. We can see that the pressure is predicted very well. In these examples, we have two regions of low pressure, but yeah, this is not very so this is one of the random effort. We see that the velocity, x component velocity is also very is nicely predicted. We also see that the y velocity of y component velocity is not that good. The prediction is not that good, and then actually we have explanation for that, because the data is not normalized. So for the network training, it was much more important to minimize the error on pressure than on the velocity in y direction. And actually, with the other example, we see exactly the same pattern. So the pressure is nicely predicted, the velocity is nicely predicted, and the velocity in y component is not that, don't have that much. And we also performed the training on 10,000 examples, and then we were able to get with an error below 1%. And bear in mind that the speed difference. So our neural network simulation is order of magnitude faster than CFD. But of course, for having this, we first need to train it on some examples. And now we are thinking about, because there are a lot of different approaches to CFD. We just shown and tested one of these with UNet. So this is the paper from November 2020. So it's a very, very recent paper, and actually what they did, they used a graph network, so it's a different architecture, but they were able to predict smooth particle aerodynamics simulation. Also, there is another paper from January this year using graph networks. They were able to show, because with UNet we can't control the resolution on wall, because the mesh is regular, but with graph networks you can have a finer mesh closer to the grid, so it's more accurate. Maybe it's more relevant for CFD. And they were able to train the network on 400 steps and roll out it for 40,000 steps. They were able to run 2 orders of magnitude faster. Also, they retain a very good behavior when they tested the network outside the set of parameters they train. And finally, I just want to say a little bit about Flowfusic platform that I'm using and developing. So basically, the platform gives you access to OpenFOAM and simulations from the web browser. We have machine learning integration. So we have some machine learning frameworks here. The platform is live from July 2020, and we are trying to on the platform we are trying to publish and to work on very interesting examples of CFD. Especially we are looking at machine learning, what machine learning can propose for CFD. So yeah, there's a support for OpenFOAM. There's also a ParaView post-processing available. There's a Jupyter notebook. There's a GPU access, and we are working on giving some code, also examples ready to go. Actually, the machine learning code that I'm showing today is available on GitHub. We will publish soon the CFD part of the process as well. Okay, yeah, and thank you very much.